Hi, and welcome to the third video on this second unit where we talk about convection. Now, convection is something that you're probably familiar with because you see it on the stove all the time, or maybe you don't see it on the stove, but it happens on your stove. It involves, and this can happen in liquids or gases, it involves hot things rising, giving off heat, and becoming cool and going back to the bottom of wherever they were. So let's talk about how this happens. Now this all stems from the physical property that hot gases and liquids have, that their particles, the particles that make them up, are moving really quickly. They're vibrating quick, they're bouncing off of each other on the atomic level. When you think about this, it makes sense that heat and this kind of quick movement go together. I mean, when you're say running around really quickly, bumping into people, I don't know, in a subway or in a dance club. Although you shouldn't go to dance club, that's for older people. You get hot. And another thing about the physical properties of being hot is that hot, quickly vibrating particles, they need more space. They really create that space around them, which also makes sense. If you think about moshers like these guys, they're twirling their arms really fast, they're jumping around against each other. They need all of this space. You couldn't have these guys twirling their arms if they were as densely packed as all these people over here. So it should make a lot of sense. When we're talking about gases or liquids, these gases and liquids that heat up, and they heat up because if you remember, a lot of heat comes off the Earth. It's infrared radiation that the Earth has transformed from solar radiation that came from the sun and is now being emitted from the Earth as it's like giving off heat. So that heats up the air close to the Earth. This air close to the Earth starts vibrating quickly. Like the mosh pit guys, it needs more space. It starts to expand. As it expands, it becomes less dense than cold air. And when you think about density, that's like how, I guess in lay terms, you could talk about something being dense as being really heavy. We equate these ideas together, but it has to do with how much matter is packed into a certain amount of area. So if the air is really hot and its hot particles need a lot of space, it's not going to be dense, and so it's less affected by gravity. Gravity works strongest on the more matter there is, the stronger the attraction of those particles to other particles is. So non-dense air is, it seeks to rise. As it rises, it gives off heat, it cools down until more or less it reaches an area where the air around it, or the water around it, the liquid around it, if you're in a liquid, is about of similar temperature. So this is the way that, I guess you could say the universe kind of regulates itself in some ways. And a similar thing happens with, a similar thing but in reverse, happens with cool gases and liquids. These are more dense. Again, think about it. You can pack a lot more people into a very small area if they're not moving at all, if they're just kind of, staying still, which is the essence of what cold gas and cold liquid are doing on the atomic level, on the really small level. So these cool gases, cool liquids become dense. There's more matter packed into any given amount of space, and so it's that patch of air or water is going to be more attracted by gravity to the rest of the matter on Earth. So it is going to sink down. So you have kind of two parallel processes going on: the hot air rising, the cool air falling, which seems to kind of simulate almost a like a conveyor belt, you could say, kind of a cycle of rising and falling. And this process is called convection. It's a really important process. It happens in water, it happens in the oceans, it happens in the air, it happens actually in the Earth's crust with kind of semi-liquid, it's like taffy-like rock in the mantle. It's so hot that it's flexible, it can expand, and so on. So the same processes that work on air in the atmosphere work on the rock in the mantle, because it's kind of it's hot and bendable, and we'll talk a lot about that in a future unit. But when we're talking about convection in the atmosphere, that's wind. Basically, just the movement of air from one place to another is wind. And when it happens in the oceans, we're talking about currents. This isn't the movement of the water, a movement of the oceans caused by, say, the movement of the moon. So we're not talking about the tides here. We're talking about kind of large-scale conveyor belts of hotter water and colder water that move throughout the oceans. And both of these processes are really important. That is the movement of hot and cold air and the movement of hot and cold water. Because, once again, they're kind of nature's way of getting back to equilibrium, getting back towards things balancing out. If hot air didn't kind of try to get where it was cooling down, and if cold air didn't try to get where it was heating up, basically hot air would stay where it was and get hotter and hotter. Cold air would get colder and colder potentially, and that would be, then you'd have a very, very extreme atmosphere on Earth. Similar things in the oceans. And sorry if I'm kind of making water and air sound like almost they're creatures with their own desires. They're definitely not. But they do follow the laws of physics. And so they kind of, that moves them around. If you've ever seen the very silly movie, The Day After Tomorrow, which is about, it takes as the premise the idea that actual real science as a whole did take seriously until a few years ago. It was a big worry that rising temperatures due to increased carbon in the air would change the atmosphere enough to melt the glaciers and the ice sheet over Antarctica enough that it would change the nature of the oceans. They would become less salty, and this would change the way that the currents in the oceans worked enough that it would shut down the conveyor belt that took hotter water to the poles and cooler water from the poles to the equator, and that once that happened, the Earth would be destroyed by a horrible polar vortex, blah, blah, blah. Anyway, the more recent experiments and that kind of thing have shown that that's bad science, not going to happen. You don't need to worry about a giant polar vortex coming down because, we mess with the oceans. But that movie does kind of apply some of these ideas. So that is that. I hope you learned a bunch, and see you in class.